great pleasure to introduce, wait, your name's not there.
No.
Francis Kirwan, who's going to tell us all about moduli of representations of graded unipotent groups and hyperquivers. Take it away.
Very many thanks. Well, since this is the final talk of the workshop, I think we should start off by all thanking the organisers very much for all the hard work that they've done for organising and solving problems and, and everything. So. Okay, so I'm going to talk a bit about moduli representations of graded unipotent groups and also hyperquivers. I'm hoping to end up with a theorem of Tommy Muller, who's just sitting at the back there. If I don't get that far, then I think he's going to be giving a talk at the final workshop, which well, anyway, he can tell you more about it. But so his theorem is about hyperquivers, and my motivation, or some of my motivation at least, comes from non-reductive GIT and GIT, which Charlotte nicely told us about just before, which is great. I'm going to start off by telling you, or possibly reminding you, about some hyperquivers, because they are maybe not familiar to people in the room, and also you can describe them nicely with pictures. So I've got a picture of a hyperquiver here. So let's have definition. So a hyperquiver well, you can define it as a directed hypergraph. So it has vertices and edges. The edges are directed, so they have an arrow in one direction, and it's a hypergraph rather than a graph. So that means that the edges come from possibly more than one source vertex. So I'm going to write it as V, which is the set of vertices, and then you've got E is the set of hyper edges, and each hyper edge has a source and a target, which, if it was an ordinary quiver, would just be a vertex, but because it's a hyperquiver, it is can be a tuple of vertices. So the source and target maps end up not necessarily in V, but maybe V squared or V cubed or whatever, but some finite number of source vertices. So yeah, so each edge has a finite tuple S of E of source vertices and a finite tuple of target vertices. So here we've got a hyperquiver with two hyper edges. I'll just call them edges from now on, I think. And so the red one has got two source vertices and three target vertices, and the orange one has two source vertices and one target. So, and as I said, an ordinary quiver, which people may well probably are very familiar with, is just the case where it's a directed graph. So you only have one source and one target for each edge. So then a representation of this, let's call it phi, of this this hyperquiver. So if it was an ordinary quiver, you'll just have a vector space. And yes, I'm doing everything over over the complex numbers. So there will be reductive groups and parabolic subgroups and things hanging around, but they'll all be over the complex numbers. I've really no idea how much would work over characteristic P. Right, so yes, so if it was just a quiver representation, gives associates a vector space to each vertex and a map, a homomorphism, a linear map between the vector spaces for each edge. So a representation of a hyperquiver is very similar, but we tensor together the source vertices and the target vertices. So it's given by for each vertex, we get a vector space, W sub V, and for each edge, hyperedge, we get a linear map, phi sub E, which goes from the tensor product over all the source vertices, which are actually ordered, so the tensor product is well defined, and then to the tensor product over the target vertices of the vector spaces, of their vector spaces.
Sorry, can I ask, are you allowed repeats in the sources and targets?
Yeah,
You are?
yeah.
Okay.
Hard
to draw, but
yes, and the theory gets a lot messier. Well, no, I mean the theory, it's there. There's maybe, yeah, things maybe get more complicated, but absolutely you can. Yeah. Yep. So right. Oh yes, and then something else is that if we've got a some group, so a linear algebraic group, say over the complex numbers G, then we'll have and this will be relevant in a minute, that phi is G module representation, call it, we'll say be a G module representation for a linear algebraic group G if each of these vector spaces is actually a G module, and each by E is preserves the G module structure as G. Okay, so having defined this setup, now let me go to the graded unipotent groups and their representations. So I'm now going to fix a linear algebraic group, and I'm going to call it H because I've sort of got into the habit of G for reductive groups and H for linear algebraic groups that aren't necessarily reductive, though this G didn't have to be reductive. So H linear algebraic group over complex numbers, and yeah, I'll probably be assuming it's connected at some point, I can't remember. So this is semi-direct product of its unipotent radical and a Levy subgroup. So U is unipotent radical, so maximal normal human unipotent subgroup, and R is Levy subgroup, so it's reductive. And so sort of would like to be interested in trying to classify these things. So I mean, lots of about classification and moduli. So yes, we want to classify these things. So reductive groups are classified up to isomorphism by discrete invariant, and so are their representations. So there aren't any moduli, if you like. But if you have non-reductive groups, so unipotent groups, for example, then you can't classify them up to isomorphism by just discrete invariants. You have continuous parameters, if you like, and so that means that you've got moduli to worry about. So reductive groups are classified up to isomorphism by discrete invariants, and also their representations. But in general, and in particular for unipotent groups, they have moduli. So the idea is to try and understand, find sort of moduli spaces. Roughly speaking, having one point in the space that corresponds to ideally to each isomorphism class of these unipotent groups, and I should have said their representations as well. And with some sort of geometric structure on the space, if you like, on the catalogue or even the canonical labeling, but you're labeling by these points in the moduli space, and you want the geometric structure of the moduli space to reflect how these vary in families in some sense. So we want to try and understand these moduli, and this is where the motivation from reductive GIT comes in. In non-reductive GIT, we think about non-reductive groups, but with a particular constraint that makes things work nicely. So I'm going to assume that H has we call internally graded unipotent radical. So in other words, I'm assuming that there exists, and it's going to be a fixed, so fixing the internal grading, a fixed grading one parameter subgroup. So one PS means one parameter subgroup. So this is, I'll call it lambda 0, and going from C star, the multiplicative group, to the center of the Levy. Central one parameter subgroup of the Levy, and we want it to have property that the adjoint action of this one parameter subgroup on the Lie algebra of the unipotent radical has all weights. So it's central in R, so the adjoint action on R, or the Lie algebra of R, will be trivial, but we want the adjoint action on the Lie algebra U to have all its weights strictly positive. So a basic example is a parabolic subgroup in in a reductive group. This property. Okay, so what we've got is that the Lie algebra of H breaks up as the direct sum of the algebra R, where the weight is 0, and then direct sum we've got I strictly greater than 0 of the weight space. Weight space is weight. Right. So we've got this Lie algebra, and then I want to assume also that we've got a representation. So let's have rho H2 B finite dimensional representation of this linear algebraic group. And so again, we can break it up into weight spaces for the grading one parameter subgroup. So we've got direct sum over the integers of and all integers now, no assumptions about positivity weights of Bj. So this is again weight space for under 0 with J. This was weight space with the under 0. And so that allows us to find a hyperquiver R module representation. So R induces well, R and rho and the other ingredients that we've got. So we get a hyperquiver R module representation. So we've got vertices for the weight spaces, or let's say the non-zero weight spaces for the grading one parameter subgroup acting on the algebra of the unipotent radical. And then we can also put vertices for the weight spaces on the representation. So let me use red for the hyper arrows. So we just want to remember the Lie bracket on. Oh, I should have put in the Lie bracket. So this is weight I plus I dashed. So we've got for each triple I dashed and I plus I dash, we get a hyper edge, which is just the Lie bracket. And then we also will have a hyper edge going from these two to this one, and the same for all other choices of I and J. So we get this this hyperquiver and this representation of it by R modules, and basically we can cover the group I did, yes, I assumed it was connected, didn't I? We can recover the group and also the grading one parameter subgroup and the representation all up to isomorphism from this hyperquiver and the R module representation, provided that we know the data that the discrete data that describes R and describes these vector spaces as R modules. So from the point of view of moduli, that really saying in moduli language, the moduli stack which roughly speaking is our catalogue or our canonical labeling or whatever, so really it's triples where H, which is U semi-direct product R, and the grading one parameter subgroup, and so the representation so that embeds as, I guess, a closed embedding into the moduli stack. We'll give it inverted commas again. The moduli stack of R modules representation of the hyperquiver. Let's just call this yes, so what's as a representation, this is given by the Lie bracket, and then this is given by the action, the infinitesimal action of the on the vector space. So yeah, so that's certainly my motivation for being interested in these trying to classify these R module representations of hyperquivers. Of course, this is a very special sort of hyperquiver, so these ones in particular. And I guess I said that this is related to work by various people in the past, in particular, well, Bernd and Trevor Jones. So they Bernd Nui looked at basically sort of algebras, and though they weren't talking about hyperquivers at all, but they were basically just looking at this part of the picture. And they were looking at the graded situation. Trevor Jones, who's was a PhD student of Dan Halpern-Leisner and the Beyond GIT program. So he is looked at the non-graded case for welfare algebras and Lie algebras as well. So both, or to some extent, related to what's going on here. And so the reason why it's nice to have this closed embedding in the hyperquivers, yeah, I should say quivers, is that the right hand side here and the left hand side have connected components. So when you fix all the discrete invariants, then you get some connected components looking like quotient, called quotient stacks. So basically, you want of an affine variety quotiented by some reductive group, which is just a product of general linear groups. And so that's nice in that affine varieties and reductive groups aren't over the complex numbers, at least aren't too well. Yeah, they're reasonably familiar. They're much nicer than stacks in some ways, but in many ways. But the so we've got these quotient stacks. So formally, somehow we're thinking of the quotient of this group action on the affine variety, but there isn't a nicely behaved quotient. So that's where GIT and potentially non-reductive GIT also can come in, because so what we want to do is understand these stacks, and the yeah, as I say, they're nasty objects because the group action is not well behaved. But so the aim, which I guess goes back to paper that I wrote with Greg Bear and Vicky Hoskins 10 years ago, I guess, and well, to some extent, Dan Malcolm Leisner's Beyond GIT program, and Andres Munez, former student of mine. So the aim is to try and decompose or stratify these stacks in such a way that the strata have nice moduli spaces, and that there really is a nice geometric space that corresponds to each piece, and also so that you can fit them together. You have some understanding of closures. So we want to use sort of GIT or GIT ideas, also non-reductive GIT, for suitable stability parameters to stratify each moduli stack, well, really to stratify this side, and then you automatically get a stratification. The one that I'm maybe slightly more interested in. So into strata, disjoint union of strata, which are sort of locally closed strata with sort of well behaved, in some sense, moduli spaces. And let's say it's gamma and reasonably sort of natural compactifications related to the closures of the strata in the stack. So it's a gamma bar. So that's sort of the ideal, the aim, and this is the appropriate thing to use, yeah. And so the first step in this program is to find, so for these hyperquivers and hyperquiver representations, and more generally really, is to try and find an analog of the so-called Harder-Narrow-Seaman type, and the Harder-Narrow-Seaman filtration of that you get from quivers, and is well understood for quivers, and extend that to hyperquivers, because then you want to stratify the moduli stack according to the Harder-Narrow-Seaman type of the hyperquiver representation, and that won't necessarily be a sufficiently fine stratification to get this ideal situation, but then you can try and go from there, in particular trying to use non-reductive GIT. So yes, so the first step is analog of the Narrow-Seaman filtration or presentation. Okay. Ordinary quiver with respect to stability parameters, which in this case just mean assigning a rational number to each of the vertices. So these are stability parameters for the action of G, which will be the group that's acting here, so the product over all the vertices of the general linear groups of the vector spaces for the hyperquiver representation. And actually you need a little bit more to define the Harder-Narrow-Seaman filtration, so you also need a norm. Need the norm on rational one parameter subgroups of G. So a rational one parameter subgroup is just formally it's like a one parameter subgroup, but the weights are allowed to be rational rather than integer. But you can construct them like you construct the rational numbers by equivalence classes of integer and positive integers. So you can think of as equivalence classes of genuine one parameter subgroups and
the condition change your rescale.
Rescale
the one parameter.
Is yes and no. That will come up later, but yes. So we have this this norm obtained. So for simplicity, yeah, I'm just going to say obtained by choosing bases. For this group, it's easy enough to say how you do it. Reach WV. And using standard Hermitian in product on the Lie algebra, which is just product of matrix is dv by dv, d where dv of wv. Yeah. Yes. So perfect question. So the Harder-Narasimhan filtration, it's really corresponds to the so-called maximally destabilizing one parameter subgroup for when you're doing GIT for an unstable phi, but those so one parameter subgroups of this group up to conjugation in the parabolic that they define, which is what comes out of the GIT picture. They correspond essentially to filtrations. So I'm just going to give some definitions of filtrations, and then I'll come back to your question. So first of all, the familiar definition. So a filtration of a vector space, which I will assume to be finite dimensional, just subspaces 0 equals w 0 1 w or w. A Q filtration well, we have exactly the same picture. We have the subspaces. But we also have rational numbers attached to them. So we start with L1, and that should be strictly greater than L2, and so on. And or equivalently, for reals, we can say FP of W is WK for that choice, the unique choice of K, which is such that LK greater or equal to P is strictly greater than LK plus 1. So so we can use the notation F dot W for the Q filtration. So if we've got these vector spaces for all real numbers, or rational numbers would be enough, and it's where the vector spaces jump which give us these subspaces and the associated rationals. And then we have the associated graded, which is, or equivalently, it's sort of the well, yes. So the associated graded is where we actually have a direct sum of the graded pieces, where it's graded pieces of the filtration. We can think of it as WK over W. They're going to, and we can identify that is the orthogonal complement to W K minus 1 in UK. So the point is that the graded version we can think of as these are the as the weight spaces for a one parameter subgroup, and then conjugating the one parameter subgroup by anything in its parabolic will give us all we will remember is the data of the Q filtration. So the filtration by subspaces and rationals, which correspond to the weights of the one parameter subgroup if it's a rational subgroup. So I am getting short of time, so I'm going to just say rather than write the link between this filtration picture and the GIT picture. So actually, I need to say what a filtration is for the hyperquiver representation first. So if we've got a hyperquiver representation, then a Q filtration of representation I of hyperquiver. So the is just we have a Q filtration for each of the vector spaces with jumps at say. So this is the union of all the jumps for all the different vector spaces at all the different vertices. And then if then it makes sense to get we can define to Q then B, then we define filtration FE one. This tensor product of these. We just take the sum over all P1 plus P2 plus PQ equals P of the corresponding parts of the filtration which so that the corresponding weights add up to P like this. So these are, as I said, these are relevant to GIT for RG, which is the product of general linear groups for all of these vector spaces, because they correspond exactly to rational one parameter subgroups of this group G up to conjugation in the parabolic subgroup determined by the one parameter subgroup. And we have the Hilbert-Mumford criterion for stability, and the refinement of that, going back to Hesselink and Kempf, to get a stratification of any affine variety with the group acting on it, because right, so yes, if I want to say this, so G acting on an affine variety, say A, then we have that X in A is not semi-stable with respect to the stability parameters given by theta, if and only if there exists a so-called destabilizing one parameter subgroup coming from the Hilbert-Mumford criteria for stability and semi-stability. So in other words, that the affine setup, we have that the limit lambda t acting on x as t goes to 0 exists. And from the point of view of these hyperquiver representations, well, admissibility, but from the point of view of the hyperquiver representations, it's saying that you have that phi e of some tensor product for its edge of say f e s w s, that's got to be contained in f of the sum e of the tensor product t in target, the tensor product of the vector spaces target, and so that's the first condition. And then the second condition is that the pairing of the stability parameters, which essentially corresponds to a character or rational character of G, and if you pair with the rational one parameter subgroup, you need to get something strictly less than 0. So this is just essentially Hilbert-Mumford for instability for the action of this product of general linear groups on an affine variety. And indeed, if the x is not semi-stable, then there's going to be there exists a maximally destabilizing one parameter subgroup for x, which is unique up to scalar multiplication and conjugation in let's call it lambda in parabolic opposite to it, which minimizes the so-called Kemp functional and so this is what we can use to stratify any affine variety which this product of general linear groups acts on. So where are we? So minimizing the functional, which this among admissible lambda to the point. So this is what, as I said, allows you to stratify any affine variety in which the stratum, which is the semi-stable locus, where you've got hopefully a reasonably well behaved quotient, and then you've got the other strata, which correspond to the maximally destabilizing one parameter subgroup up to conjugation. And so we can, in order to understand this this stratification, we really want to understand these filtrations, or Q filtrations, which are uniquely uniquely determined. Well, possibly up to scalar multiplication, but then you can also put in some normalizing factor, for example, because this is homogeneous, but you know that if you've got instability, then this is negative, and so you can rescale to fix the thing on the top to be -1, and then you just minimizing the norm on the bottom, for example. So you can choose a particular representative. So basically, these Q filtrations are giving you are telling you which stratum so the sort of the type, the discrete data of the filtration, the dimension of all these subspaces in the vector space is giving you essentially the type of the stratum that you belong to. And so what happens is that in the quiver setting, this is really well understood, and you have any quiver representation has this uniquely defined Harder-Narasimhan filtration, and it's in principle it's a Q filtration, but in fact the rational numbers that are associated to the terms in the subspaces in the filtration actually are essentially determined entirely by the dimensions of these vector spaces together with the stability parameters theta. So although in principle it's a Q filtration, in fact it really just comes down to a filtration in the quiver case. And so I don't have time to write out the details of Tommy's theorems, but Tommy has a nice description of the analog of the Harder-Narasimhan filtration for hyperquiver representations, which where you have so you're looking at all the admissible one parameter subgroups or admissible filtrations, so they're having to satisfy this condition. So for an ordinary quiver, it's just saying that FPWS gets sent to FPWT, but it becomes much more complicated a bit more complicated anyway in the hyperquiver case. And in the quiver case, then we have essentially the everything is just determined, as I said, by the dimensions of the vector spaces involved in the filtration, together with the thetas. And you have constraints on those on the slopes involving those subspaces. And in the hyperquiver case, it becomes more complicated because you have to, but you've still got sort of discrete data together with the subspaces, which in terms of the sort of which of the weight vectors, weight spaces, as it were, in the source for the hyperedge gets mapped into which of the ones for the target. So yes, sorry, I have overrun and have not got as far as I wanted to, but anyway, I will stop here and thank you very much for your attention.
I think I'd say you've got exactly far enough for us to look forward to Tommy's talk now.
Right,
Tommy can
exactly.
fill in all the details you let me know. Right, do we have any questions?
I have a question regarding motivation. So I've seen sure about Moduli, but the talks exactly what they do with what you were saying, not with a hyperquiver, which I had to learn while I was listening what it was, but have representations on a quiver, and then I've seen it studied to actually, for instance, study singularities or things like this in work of Alicro.
So quivers do turn up in lots of situations, and also they are very nice things to study from a GIT point of view. So
does this happen with hyperquivers? They have like appear in geometric situations that you would expect.
Well, I mean, the motivation that I started with, and which is has been my main motivation so far, is to understand these moduli of unipotent or graded unipotent groups and their representations. And the reason for wanting to understand those is that if you go back to the general aim for, if you've got a moduli problem or a moduli stack, to try and stratify it into pieces that have nice moduli spaces, and then you can really try and understand. That involves, so hopefully you've got some description of your moduli stack as at least a sort of increasing union of open substacks, which can be described as quotient stacks. And then if you want to understand a quotient stack, then even if you're starting off with something quotiented by a reductive group like this product of general linear groups, the way to stratify it involves this sort of instability stratification that I was talking about, looking, or at least first of all. And so then and yes, I mean, something that I should have said is that, of course, you can say, well, I just want to look at the semi-stable locus, and if I understand that, then that's good, and too bad if there are unstable things that I don't understand. But the trouble is that it might well be that the semi-stable locus is empty, and I mean, and in particular, if you have the semi-stable locus for these hyperquiver representations, that might be non-empty, but then if you intersect it with the part that corresponds to the unipotent, graded unipotent groups and their representations that I would like to understand, then it might be that the semi-stable locus doesn't even meet that the part corresponding to that I want to understand. And so the advantage of wanting to find a stratification so that you can understand all the strata is that then when you restrict, the stratification will still restrict to a nice stratification of the thing you really want to understand. But the trouble is, when you're looking at the strata that appear in this instability stratification, then you can no longer use ordinary GIT to try and construct quotients of them or of open subsets of them, because just by definition, they're unstable strata, so you can't try and you can't do the standard look for semi-stable locus unless you're able to shift the stability parameters. But if it's a semi-simple group, you can't shift the stability parameters necessarily. And so what you can do is the stratum initially is a quotient by the full reductive group, but it turns into a quotient by a parabolic. These parabolics turn up all over the place. So then you want to say, okay, well, the parabolic, I've got lots of characters. I can do some shifting and hope to get some semi-stable points, but then you're working with a non-reductive group. So that's why the non-reductive GIT comes in, and then when you're trying to do non-reductive GIT, then these graded unipotent groups come in as well. And so what I would really like is, I mean, it might be possible, it might not, is to have if you can really understand the moduli space of all these, or the moduli stack of all these graded unipotent groups and their representations, then you could then sort of plug that into any other moduli stack that you really wanted to understand by using this non-reductive GIT picture. So yeah, that's the main motivation. But these hyperquivers are also nice in their own rights. But yeah, I mean, there are other examples of hyperquivers which Tommy can tell you about.
Okay, were there any other questions? If not, let's thank Francis again.